Welcome to our presentation of fast task planning with neuro-symbolic relaxation. Real-world task planning often demands long-horizon reasoning over large sets of entities with complicated relationships and attributes, which creates a combinatorial explosion during searching that overwhelms classical symbolic planners. For example, let's consider a real-world maze navigation task. Boxes are seen as heavy and pushable obstacles. Bottles are seen as light and graspable obstacles. Chairs are seen as immovable obstacles just like walls. To reach the goal position, the robot needs to move away the bottle before pushing the box, and push away 2 boxes before reaching the goal. Here's a possible solution for this task. This kind of task can be converted into a discrete PDL planning problem similar to this picture. Classical planners like Fast Downward can spend several minutes expanding useless nodes without providing a feasible plan. A strong baseline ploy shrinks the search space by gradually filtering out important entities, but it sometimes ignores critical entities and gets stuck on an unsolvable simplified task. In contrast, when applying our Flax, a correction mechanism ensures the solvability of the simplified task. As we can see here, an important entity is recovered. We designed 4 difficulty levels for this domain, and in the hardest expert mode, our approach Flax significantly outperforms these 2 SOTA baselines in both success rate and planning speed. Although in this domain, Flax is trained exclusively on grid-structured layouts, its neuro-symbolic relaxation strategy generalized to irregular non-grid workspace. At runtime, we tag every rigid body with a semantic class and extract the center of its bounding box. Each center is mapped to a symbolic position. However, real-world environments often contain large free areas. If left empty, they can block the symbolic search for valid paths. We therefore sample additional stepping stone positions by packing equal radius circles until saturation. After sampling, the new positions are merged with the original objects and positions to create a new PDL task, which is then supplied to our Flax pipeline. Here are more examples of task planning in i16. We also did real-world maze navigation experiments using a unitary go-to quadruped robot, equipped it with a 6DOF-D1 manipulator. Our proposed Flax is a fast yet reliable neuro-symbolic relaxation strategy to accelerate task planning. Our key insight is that let the fast neural module guess boldly, and the reliable symbolic modules will watch its back. Next, I will introduce our full pipeline. In the pre-processing phase, the raw task is lifted to a typed PDL instance and converted into a scene graph. In the training phase, we run an optimal symbolic planner once per task. Mark every entity used in the optimal plan as important, score is 1 and others 0, and train a GNN to predict these important scores with a binary cross-entropy loss. In the inference phase, we invoke 3 steps within the global time budget. In step 1, we first use the GNN scores to keep only high-scoring entities, plan with symbolic planner, and progressively lower the score threshold until either a valid plan is found or time for step 1 runs out. However, step 1 may exclude some important entities, rendering the simplified task unsolvable. To discover such omissions quickly, we solve a rule-relaxed version of the original task and add any newly involved entities to the stage 1 set. Finally, we apply lightweight complementary rules for local consistency and then plan once more on this final simplified task to get a solution.